So I'll draw a picture of the situation, starting with part A here. So I'm going to hang a vertical spring and then put a mass on it. Now in part A, it's being held at rest and the spring is not stretched at all, so x equals 0. Need to calculate the sum of the gravitational and elastic potential energies at this point. So anytime you are calculating gravitational potential energy, you have to specify where the reference level is going to be. And I can choose anywhere I want the reference level to be. And I'm just going to choose it right where the box is. That'll make it easy. So this will be my reference level right there. And by doing that, my gravitational potential energy is simply 0 joules. mgh. Mg times 0 meters will be 0. And my elastic potential energy, it's half kx squared, but as we said, the spring is not stretched at all. So that's also going to be 0. So the sum of this is really easy. 0 plus 0 equals 0. Okay, so that's part A. Part B, we're going to let this go, release this from rest, and it'll fall down. Okay, it'll fall down and cause the spring to stretch, and it says it's stretched by 5 centimeters. So it stretches by a bit, 5 centimeters. I have to keep the reference level the same. Okay, my diagram's not the greatest here. Let me try this again. Okay, this is a 5 centimeter drop from where it started. There we go. So I'll recalculate everything. So I'll do gravitational potential energy first. That's mgh. So that is 4.0 kilograms times 9.8 newtons per kilogram times negative 0.050 meters. Need to use meters when we're using the mgh formula. And it's negative because it's now below the reference level. So that adds up. Well, let's put that in the put that in the calculator. So I'm getting negative 1.96 joules. Now we'll calculate the elastic potential energy. The formula is half kx squared. So that's a half. The spring constant is given as 800 newtons per meter. And how much it's stretched by is 0.50 meters. Have to square that. So I'll put that in the calculator. And I get positive 1 joule. Sig figs, looks like there should be 2 sig figs to both of these. So when I add this together, that'll be negative 0.96, which actually should be goes to 1 decimal place. Use the addition subtraction rule for rounding. Okay, so that's the sum in part B. So in part C, they ask, why are the answers to A and B different? So we had a sum of 0 joules in part A, and now we have a sum of negative 0.96 joules in part B. Why are they different? Shouldn't they be the same? Due to the law of conservation of energy, the total energy needs to be the same. Well, the answer is we actually have not accounted for every single type of energy here. As this block is let go, well, it's moving now. So this difference, this 0.96 joules difference must be because we haven't not accounted for the kinetic energy yet. Okay, so I'll just say there must be, it would be positive 0.96 joules. Kinetic energy is always positive anyway, of kinetic energy. at part B. Okay, that'll make it add back up to 0, which was the total amount of energy we had in part A. And this is assuming that we're ignoring other energies, like we're ignoring thermal energy here. Like a tiny bit of it might be thermal, but we'll just ignore that and just say the rest of it had to be kinetic energy.